In our last video, we have derived the Newton's second law of motion in this non-inertial frame of reference dqn. It is useful to describe the motion. In fact, it's a circular motion of a free particle, but it's less useful to really describe the motion of electric machine's rotor. And the electric machine's rotor is really a rigid body. In this video, we are going to study the angular motion of a rigid body. The difference between a rigid body and a free particle is that we have constraint force that's applied to any point mass in this rigid body. So assume this is a solid mass with a lot of point mass dm here. So dm has some neighbors. So those neighbors, they are really applying some constraint force to make sure dm stays in place. So such that the rigid body does not deform. So we need to resort to this Euler's rotation theorem. It states that if the rigid body is self-spinning, self-rotate in space, there must be some fixed point inside the rigid body. We need to place our origin of the Cartesian coordinate system to this fixed point, and we can then derive the rotational version of Newton's second law. So we basically have omega vector going through this fixed point. To see that, we need to first have this position vector r. Note that the length of the r cannot change because it's a rigid body. Any distance between 2 points in this rigid body does not change over time. By assuming that any force that's in this parallel direction, it's not effective. It's basically useless. It has no effect to the motion of our rigid body rotor. But any force that's orthogonal to this position vector r, it's effective force. And it's implying that we should reuse this cross product between vector r and any force vector f to describe the effective force. So the effective force is known as the torque. And we can derive the equation for our torque here. So this is torque. So basically we take the cross product to our position vector at both sides of Newton's equation. A trick here is that we add and subtract the same term here. So this is actually really equal to 0 because d by dt r is equal to v, and v times v cross product v is really equal to 0. So we basically are adding a 0 and minus a 0 here. And here we derive this term because there's a cross product rule for our time derivatives. So that's basically so let's say we have r times v. It's evaluated into d by dt times r cross product v plus r cross product dv by dt. So by doing that, we have this term here. So and note that r cross product v is equal to r cross product the result of r cross product omega. Omega is really the angular speed of our rigid body. Note that they are orthogonal to each other. So this is r, and this is omega. So it is equal to r squared times omega. That's why we have this result here. And by doing that, note that omega and t, they are parallel to each other. They vector along the z-axis. We derive this 1 degree of freedom result as our rotational version of Newton's second law of motion. So this is only valid to a particle m. We assume the point particle is of mass m. Its rotational inertia, it's no longer mass. It's calculated as mr squared, denoted by symbol j. It's called moment of inertia. So remember, this is only valid for a point mass. So if we want to derive the motion equation for our whole rigid body, we need to integrate equation 15 over the whole volume of the rigid body. By doing that, basically we are summing up all the equation of motion for all particles inside this rigid body. Technically speaking, let's consider our rigid body is a cylinder. So it's a cylinder, and we are going to, it's basically basic calculus. If we want to calculate the inertia, moment of inertia of this cylinder, we need to assume there's a ring. It's an infinitesimal ring with a thickness as dr, and we integrate it over from 0 to the radius of our cylinder r. Yep, basically we are doing that. So assume that our cylinder, it has same density all over the place. Its density can be calculated as pi r squared. So we denote the result as Js. S stands for the shaft. So it's the moment of inertia of the shaft. And we are going to decompose our sum of torque into two kinds of, from different into two sources. They are electromagnetic torque and load torque. So let's substitute the result in 18 and 17 into formula 16. We reach this it's well-known rotational version of Newton's second law for shaft, rotating shaft. So the angular speed is the time derivative of the angular position of our cylinder theta. So if you look at figure 1, so yep, this is theta here. And we have some further results regarding the energy and power when our rigid body is spinning. So the power, it's the motion kinetic energy is 1 over 2 times Js times omega squared. And the power is the torque times angular speed. Note that we are talking about the mechanical input torque. So this TEM here is really not our mechanical input torque. This is generated by our electric circuit, which we will discuss later. So the mechanical work done by the mechanical input torque TL is the integration of the power over time. So note there is a negative sign here. So when TL is larger than 0, it's actually taking away energy from our system, which means the energy is from our electromagnetic torque to load torque. And this kind of energy is from our voltage times current. So which suggests that our electrical machine is really converting our electrical power into mechanical power. In next video, we will further discuss the electrical dynamics part of our model.